Okay, let's start today's lecture. Do you have any questions before we start? Anything? Any questions? Okay, so we were doing mathematical induction. I would like to do 2 more examples and give you a little stronger version of induction, like something slightly different. So today we have 2 hours. The second hour we'll start doing something called division algorithm and Euclid's algorithm. So we'll start doing some number theory. If I can finish everything I would like to give you a homework set for next week, Tuesday. And we'll have a quiz on Tuesday on that homework set, as we discussed earlier. So when I'm giving the homework set, I will explain this again. But okay, let's start with this example. This is the example on mathematical induction. Prove that there are 2 to the n subsets of a set consisting of n elements. Okay, so n here is a positive integer. It could be 1, 2, 3, 4, any number. And some of you probably have a feeling for this. We can write some examples. But the point is, you're supposed to show it for any n. So we can't just say it's true for 3, 4. We need to show it for all n. Okay. So just to illustrate it, for n equals 1, you could be talking about a set like this. For n equals 2, you could be talking about a set like this. For n equals 3, you could be talking about a set like this. Okay. Now, what's the subset? A subset is a set which you can form by elements of this set. So, for this set, for example, we sometimes denote this with P, power set. The subsets are, we can actually list them like just this is your set, 3 elements. So this is with 1 element. This is with 2 elements. Okay. So if you list the subsets, for example here, this singleton with only x1 is a subset. Singleton x2 is a subset. The entire thing is a subset. Is there any other subset that I should list? Empty set is a subset. The notation for empty set is this. So a set which has no elements is called an empty set, and it's a subset. So you see that there are 4 of them here. Here it will be just this and this. So there are 2 of them, which is consistent with what the claim is. For this one, you can list all of them. Empty, x1, x2, x3. They're doubles like this. And all 3. So how many you see here? 1, 2, 3, 4, 4, 8, right? So 8 of them. 8 is 2 to the 3, so it's again consistent with what the claim is. If you wanted to show this for every n, do you see any argument? Any way to verify this. Why it's always 2 to the n? Do you know any proofs or any arguments for this? Combination, choose n, sum of n choose i's or something like that. Any direct argument that will not use combinatorics. Any?
We are adding the new elements to all subsets, and it's n plus for doubles. And when we add the third element to all subsets, we get the other subsets with the third element.
So basically seeing this 8 as 4 plus 4, like this, and exactly half of them belongs to the earlier set. Since we are adding the last one to all these things, you get exactly twice as much as the previous case. That's good. Can we write this as an induction proof, or can you use some form of induction? Because this is saying each time it doubles, but suppose that is true for n.
I think it's the method for how it's increasing. I think we can write 1 or 0 for each element, like a binary. If we include this one, it will be 0, 1. Otherwise, 1. And totally, it should be 2 multiplied by 2 multiplied by 2.
Let's call this solution 1. Let me write your solution first, and then we write your solution. So the binary code is a way to write subsets in 0-1 sequences. Since you are engineers, you're familiar with this. So basically make a correspondence between these and 0-1 sequences. So to form a 0-1 sequence associated to these, best choice is basically use 3 digits, right? And then declare first digit, second digit, and third digit as some answers to a 0-1 question. Is it what you wanted, or something?
Actually, I think it's not. I think about the.
You're saying an AND operation.
Sorry?
Yes.
Huh?
He's talking about an AND operation.
AND operation. I mean, this is almost like an AND operation. I mean, I thought you were trying to get to this, but if we wanted to do this way, can we do it like, so we want to use 3 digits and use 0 and 1. Can you find a good way to code the information on the left-hand side, on the right-hand side, using 0-1 sequences? Subscribes. Like for example, if I said this is this, and this is this, what does it mean to have this? So the first one, the question is x1 is an element? So if the answer is yes, you get 1. If not, you get 0. And the second one, the questioner says, is x2 an element of that subset? And this one, is x3 an element of the subset? So
There must be another definition for empty
so,
There must be another definition for empty set.
Why? Empty set is the one that you get no, no, no as answer. So you get 0, 0, 0.
Actually, what I'm saying was, let's consider the third one.
Uh-huh.
For each one, it could be inside, or it could be my subset or not. I assign 1 or 0 two possibilities. For each two, it's two possibilities. If there are two possibilities, there are if n terms, I just multiply. Yes.
So you're saying 8 comes from the fact that for each of these digits, you can either put 0 or 1. That means you have 2 choices, 2 choices, 2 choices. So that's why you get 8. But you have to make sure that this codes, 0, 1 codes, actually gives these information uniquely. That these subsets, they don't have like 2 different things giving you the same number, or 2 codes doesn't go to the same thing. So basically you need to verify or sort of say that this is a one-to-one correspondence. Okay? So that the counting on the left-hand side coincides with counting on the right-hand side. So with this, what will be the number here if x1, 1, 0, 0. Second one, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1, 1. So did we get all the sequences? Any sequence will give you a subset, right? And every subset will give you a sequence. So you are not missing any subsets. And these things are actually exactly 8 of them, because you have 2 choices on each of these places. So this solves it. I mean, this is the solution, right? So for arbitrary integer n, and we will have a one-to-one correspondence between subsets of this, let's call this an, and 0, 1 sequences with length of a sequence is exactly the number of digits. Okay, so with length n. Since there are 2 times 2 times 2, exact n of this, 2 to the n such sequences, there are exactly 2 to the n subsets. That's what it's. So this is direct counting. You count something by using some correspondence to something else that you can count much easier. Solution 2, I mean, you don't need actually another solution, but since this is a good example for induction proof, I will give you another solution. This solution 2 is how you write the induction argument. So we can try to write the induction argument. You can use this observation that when you look at subsets of a set an, some of them will have xn plus 1, and some of them will not have that. So we can group those subsets of an plus 1 into 2 subsets, 2 groups, and then count them separately. So basically, the idea is so proof by mathematical induction. Is it to do? So first check it. check that it's true for n equals 1. You can even check it for n equals 2 if you want, and check n equals 1. In this case, we have n is 1, so this set A1 is this, and subsets are empty set nx1. So we have 2 to the 0, 2 to the 1. 2 to the 1 subsets. So it's correct. 2 to the 1 is n equals 1, so it makes sense. So this is the first check you do. Second, remember we need to show whenever an is true, an plus 1 is true. Okay? So I assume an is true. Assume this statement is true. Number of elements in an is equal to 2 to the n. Okay? So here an means x1, x2. Okay? So consider an plus 1. So this is your set, n plus 1 elements. Now count the subsets of this. Let P be the set of subsets of an plus 1. Now the argument was this set of subsets of an plus 1. So here, this is your an plus 1. So this is n plus 1. This is n. So exactly half of them has no an plus 1 in it, no xn plus 1 in it. The other half has xn plus 1 in it. So a subset B inside an plus 1 either has this last term xn plus 1 in it, or it does not include that element. So it's either of them, like either that or this. Either it has it or not. Now, if you have a subset which doesn't have it, you can add it to get a subset which has it. If you have a subset which has it, you can take it out to get a subset here. So you can form a one-to-one correspondence between these sets and these sets. Okay? We can form a one-to-one correspondence between these two groups, these two types of subgroups. By basically adding the last one to the subset, if it is not there. So what this tells us that number of elements in an plus 1 is exactly twice as subsets of an plus 1. So this is number of subsets, which does not include xn plus 1. So it's exactly 2 times the number of things on this side, the ones that doesn't have x3 in it. So can we say something about that number? What's the number of subsets of an plus 1 that doesn't have xn plus 1 in it? Why? Why is 2 to that? Because, let's say one more line, because it's exactly the number of subsets of an. Okay? So this thing, if they don't include this, that means you can sort of look at the rest to form those subsets. But the rest is an. So that number is number of subsets in an. Because we know they don't include this. So that means they're subsets of this set. Okay? But now, we can use induction. So by induction, I can say an is this. number of elements in A instead. I'm using a bad notation, sorry. This is the power set of A. Number of elements in subsets of A. So it's 2 to the n. But now you get 2 to the n plus 1. Okay? So this is what I mean is power set. The subsets.
Can you use this solution to, are you supposed to prove for n equals 0?
For n equals 0, what does it mean? You have empty set, n is 0, and you have only one subset. So it's still true for n equals 0, but we start with n equals 1. Because of we sort of think this is starting with n equals 1, I start with n equals 1. Okay. Any questions about this? It's important how these are written too, right? This is a good illustration that induction proof doesn't mean that you have to do arithmetic. I mean, there's simple arithmetic here with multiplication by 2, but there's more difficult part is setting up the question, setting up the pieces, and so on. So this is an induction proof. Okay? Example. Most of the engineers like the first proof. But so if you had to do one of the proofs, one of the solutions, which one you will prefer? One? How many people want? Yes. Okay. How many people? 2? Okay. Good. At least some of you. I also prefer 1 in some way, but this is a little bit premature. Like we'll learn more of counting. This is about counting, and we'll learn more complicated counting arguments. And that's the nice part about counting is you can sort of be creative with things. Okay, one more question, and then we'll finish this. So this question I'm going to write. Maybe some of you have experience with this. It's about recursive sequences. So we have this sequence of real numbers indexed by integers, which satisfy this rule. Okay, so as you see, the question is, given a sequence, so from calculus, I probably remember sequences. So the sequence means integers, like real numbers indexed by integers. So this is the first term of the sequence, second term of the sequence, and so on. The difference here in the recursion, the next term of the sequence for n equals 3 has to be calculated using the previous 2 terms. So each time you need to know an, you need to use the previous information. And this initial values, 2 values, and this equation, you need to determine what an is for all n. So we know what an is from these equations. But now the question is find an explicit formula. Okay? Something like 3 to the n, or maybe n plus 1, some explicit formula. Any guesses so far? If you calculate a couple of terms, maybe you can see. So the best way to guess is to calculate a couple of terms, like calculate n equals 3, 4, 5, 6, and so on. And try to guess it, what an is. So A1 is 3. A2 is 7. These are given already. Okay. So now I need to calculate A3. So A3, it says it's 3 times A2 minus 2 times A1. So what is it? Huh? 15. So it's 3 times 7, 21, minus 6, 15. A equals 4. 3 times AN is 3. 2 times A2. So what is that? 20? 21? 45 eksi 14. 31, yes. A5? 3 times A4 minus 2 times A3. 93 minus 63. Okay. So, anyone who wants to make a guess? So, what is the formula for this one? 10?
Multiplied by previous one by 2 and add 1.
N equals 2n plus 1.
We need a formula. Not.
N equals 2n.
So for n, you're claiming, this is our claim, is 2 to the n plus 1 minus 1. Does it work? For 5, you get 2 to the 6 minus 1. 64 minus 1, 63. For 4, you get 2 to the 5 minus 1. 32 minus 1, 31. So it's the formula. Okay, so that's our claim. AN is that. Okay. Now, we are in the second part. Prove. Just, prove it by using anything you have. How can I prove such a statement? Because we made a guess. Maybe it's the wrong guess. Maybe after 6 it won't work. I mean, even you check this for until 1 million, it may be the fact that next one is not true. So. And if satisfy the formula, that's one solution. Let's write that. Solution 1. AN equals 2 to the n plus 1 minus 1 satisfies the conditions. I mean, basically, you can check if 2 to the n plus 1 minus 1 is equal to 3 times 2 to the n minus 1 minus 2 times 2 to the n minus 1. If this is true, then we're done. Is this true? So this is the question. 3 times 2 to the n minus 3 minus 2 to the n minus plus 2 2 to the n minus 2 to the n is 2 times 2 to the n. Minus 3 plus 2 is minus 1. So I get 2 to the n plus 1 minus 1. So that's true. It checks out the formula. Initial values are correct, right? So you can check, we already did. N equals 1, 3 is equal to 2 to the 2 minus 1, n equals 2. You get 7 is equal to 2 to the 3 minus 1, so they both check out. So it works. It's a solution. We don't have to also know its solutions are unique, and you don't need to check if there's any other one, because it only says find one. So that's actually works, right? Because it checks out. That's the solution. Okay, so can we do a second solution like we did before by induction? We can try to guess what?
What is an plus 1?
Uh-huh.
If it is 2 to the n plus 2 minus 1, then our...
So we can assume this formula checks out for all the numbers until n, and then try to verify the n plus 1. And then we can try to, so let's write this by mathematical induction. Okay. Now, what we will try to do is so assume, like first check the lower values. Which we see that A1, 3 is equal to 2 to the 2 minus 1. So we are trying to show an plus an is equal to 2 to the n plus 1 minus 1. This is what we're trying to show. This is for all n. Okay. So we check it that it works for n equals 1. So I assume it's true for n. For n. And we want to verify n plus 1. So how can I do this? How can I verify it's true n plus 1? So this is what we want. What's a reasonable thing to do?
You can change the formula.
We can use the formula to calculate n plus 1. So the formula says it's true. You just shift the formula by n, that's y1. So the formula will become like this. Now, because I know the value for an, I can set it up 3 times. What's the value for an? This, right? So I can put it here. Now, to get the an plus 1 using this formula, you can use an, but you also need an minus 1. But I don't have an minus 1. I only have an. So how do you solve this problem? But I don't know what an minus 1. I only know assume it's true for n. I didn't assume it n minus 1. I only assume the previous one is true. So if in terms of blocks, if I explain, I only assume that if a block falls, the next one falls. But here I need 2 blocks falling before so that I can tell if a block is going to fall. So this is sort of a situation. Let me draw the blocks. You think about this. So remember we had the dominoes. And let's say n equals 1. So induction said first domino false. This one is true. So this is the mathematical induction. second, we said Sn is true implies Sn plus 1 is true. Then, by mathematical induction, Sn is true for all n. See, it strictly says the only thing you need to know is that if a domino falls, next one falls. This is all you need to know. And this works. But what if you cannot conclude that next one is falling by just knowing previous one falling, but you need two terms before n falling? Which means we have some sort of resistance dominoes. They only fall if all the previous one falls. What if we need to know? This sometimes we know all the previous one had fallen. This can happen. This happens a lot of the time, actually, when you're verifying things. Like knowing just the previous one is sometimes not quite enough. You need to all the past information, all of them. Like not sometimes 2 terms, sometimes 3 terms, sometimes all of them. And in terms of logic, there's no problem of assuming that, because we actually know that if first one falls, when you come to n minus 1, all the previous ones already fallen. So you actually know that. You just need to set it up right. Okay? So we have this different setting. It's called strong mathematical induction, where your statements are slightly different than this. Okay? So you're replacing this with, I call it 2 prime, with the statement that you can show n plus 1 is true under the assumption that all the previous ones are true. Okay? So now your 2 is different. Your 1 that doesn't have to be different. It's like, but your 2 is different. This is called strong mathematical induction and very extremely useful. You can easily verify that this is equivalent to this, but it's very handy. So the strong mathematical induction, if you ever need to use all the previous experiences to verify a statement, you set it up with the strong mathematical induction. Okay? So now I can use, by strong mathematical induction, this is this. So this is the assumption. And we change this. So assume that AK is equal to, or AI, is equal to 2 to the I plus 1 minus 1 for all I, 1, 2, n. So not only for n, you assume it true for all previous ones. By assuming that, now you can put this here. Okay? Any questions? Does it make sense? I mean, it looks like a I don't know. It's essentially the same statement, but you have to set it this way. Okay, so to complete it, you just calculate this. We already calculated this in the other example. So we get this. Any questions? Anything?
Pek bir farkı yok mu sanki? Çünkü şeyde matematik induction'da S is true for all en büyük eşit değil demişiz.
Şurada mı? But this is your conclusion. Conclusions are same. Conclusions are same. But because the two is different, this gives you a more powerful technique. If we were just using this, we wouldn't be able to get that. So only using standard mathematical induction, you cannot say this. That's the difference. There's strong mathematical induction. You need to start with a stronger statement. You need to know all the previous ones are true to get the next one.
Burada A harfileri bulabilmek için önceki ikisinin doğru olduğunu bilmemiz gerekiyor ya. İlk başta S1 ve S'nin doğru olduğunu gösterip
okay, I have to translate this question. Can you ask in English if possible? Or I don't want you to get shy about it. If you I can translate too, but because we can't follow everyone.
If you want to find A n plus 1,
Yes.
We need to show that we need to know that Sn and Sn plus 1 is
Exactly.
true. So if you show that in the first step, if you show that S1 and S2 is true, then we again can reach that Sn is true for all and
I mean, you have to think this way. This statement says that if you check these two, you get this, okay? Now, can you check 2 for this case? Can you show 2 is true in this case? You cannot, because you can never get Sn plus 1 just using Sn. So 2 is not correct. 2 is not verifiable here. You cannot verify 2. Okay? For this example, you cannot verify 2. Because we cannot verify 2, we cannot conclude what he says. So this becomes unusable. You cannot use this.
If we assume that both Sn and S minus n minus 1 is true.
Strictly using this algorithm, take this as a computer algorithm. It says this through this through this comes out. But you cannot feed this. I cannot verify this statement. So I cannot get the output. So I change the statement. I can change it to a 1 that I can verify. Now I can verify 2 prime. So now I can conclude the same thing. The only difference is I made the verifiable statement instead of the old one.
So when you say that both Sn and Sn minus 1 is true, then we had a different version of truth.
We could have written a version, yes, exactly, which only requires first to Sn and Sn minus 1 true, and the conclusion is...
Because in this question we have groups which are includes only 3 elements.
But then it wouldn't work for the ones which has 3, 4, and so this is generalized to full level, that anytime you need all the previous statements to justify a statement n plus 1, you use this version. Okay? I wish I had more sort of onto the point examples. Maybe I will try to find other examples later. This is the only example I often do.
How could we prove strong mathematical induction?
How do you prove strong? It's a good question. Can you prove strong mathematical induction using mathematical induction? Yeah, that's it. So this looks like the weaker assumption, right? 2 prime is harder to verify, I mean easier to verify than 2, so maybe it's not true. So how you verify strong mathematical induction? Using mathematical induction. Can we do this?
Maybe it's easier to strong mathematical induction by strong mathematical induction. Some recursion.
So how can you prove strong mathematical induction using mathematical induction? So set up something. Change the statement.
Can we think about the strong mathematical induction as a reverse way?
Reverse way.
Like,
Which?
If S n plus 1 is true, then S1, S2, and so on.
Well, we don't really know that direction. I mean, knowing this direction doesn't mean we know other direction as well. But what you're saying, I mean, actually, one should be asking also why this is true as well, right? I mean, we said if this is true, but you also want to prove why this is true. Is there something stronger that gives you why mathematical induction is true?
It can be proved by block theorem.
With pictures, but
Can we prove by logic? Fully logical.
there's actually a proof why mathematical induction true. I can give you this proof, but that also uses something. So you cannot prove it without having anything. You can only prove it by knowing this statement. Every non-empty subset of positive integers has a smallest element. An obvious statement, you may think, but that's what you need to feed in to get mathematical induction. This is called Ware ordering principle. So let's call this Ware ordering principle of integers, positive integers. Just Ware ordering principle. So now it's 3 implications. Can you show mathematical induction using this principle? Which will come to what you just said. So we'll argue backwards, basically, but that's what we... I often don't tell these parts, but let's see if we can do it. So if you know this principle, can you show mathematical induction holds? That mathematical induction is a true thing. So that means if you have S1, S2, Sn, all the statements, if you verify this, then it's always going to tell you Sn for all n. Using this principle. It's a very nice practice in logic. You can try. I mean, it doesn't have to be correct in the first time. Somebody will say something, somebody else will say something.
If every set has a smallest element, then we can check the condition for this smallest element.
Mm-hmm.
And in this condition, we can use the assumption, and we can make assumption and check for the Next.
Mhm. Previous one. Right? So you have all these statements, right? You want to verify. We are claiming that all of them are true. Just knowing these 1 and 2, claiming all of them true. If it is not the case, if it is not true for all n, what will happen? It will be false with some n. So that means some of these are bad. So mark the ones which are bad. Some of them are bad, right? So call them the bad ones. Let's call it I. So those are the bad ones, false ones. This is a non-empty subset because of the claim that at least some of them are not true, right? So it's a non-empty subset. So this is a non-empty subset. This set is non-empty. And it's a subset of positive integers. So what does it tell me? That it's a non-empty subset of positive integers. There should be a smallest one. There should be smallest bad apple, smallest bad thing. Right? So out of the ones that Sn is not true, find the smallest one. Okay? Then there is the smallest one. There is the smallest element. Say k in I. So sk is the smallest one. Sk is Sn is not true. So we use the principle. But we know this, okay? Don't forget, we know this. From this, we need to get something like illogical. Can you have a smallest one which is not true under this 1 and 2? Look the previous one. What does it the previous one says? What can you say about sk minus 1? Yeah, it is smaller than the smallest bad apple, so it must be a good apple, right? Then sk minus 1 is true, because it's smaller than the smallest bad one. But if sk minus 1 is true, by 2, sk is true. Okay? Sk is true. We found the illogical statement. We found the smallest bad, but we show it's not bad. But we took it as the smallest one. There is always a smallest one, but the one before the smallest one has to be true, but that will push back this one is true. The statement 2 always pushes things back. So whenever you find the smallest one, the one before that will push it back. Of course, you have to check this smallest one is not S1, and that's because you have to check 1, because you have to find the previous one. So that's why you need the 1. S1 must be true. So you know that bad apple is never S1. So the bad apple, anytime it's SK, previous one has to be true, but this is true always implies this one is true, so you get a contradiction. You get like illogical statement. I think overtime this. Okay, think about this. We take a 10-minute break and continue with something else.